It started with a flicker on a weather satellite feed, something that most people would have scrolled past without a second thought. A swirl of clouds, a patch of pressure that didn't quite look right. But the meteorologists watching that feed didn't scroll past. They leaned in, and then they started making phone calls. What had just formed wasn't one storm, it was two, and they were heading directly for each other. In the history of modern weather science, forecasters have tracked thousands of hurricanes, typhoons, and cyclones. They've watched systems grow from tropical depressions into catastrophic monsters. They've modelled worst-case scenarios on supercomputers and run the numbers until the numbers stop making sense. But what is happening right now sits in a category that very few meteorologists have seen in their careers. A double monster storm event. Two massive concurrent systems interacting with each other in ways that the models are struggling to predict. And that struggle, that gap between what the computers say and what the atmosphere is actually doing, is exactly what has forecasters terrified. To understand why this is so unusual, and why the people whose job it is to stay calm are not calm right now, we have to go back to the basics of how these storms form in the first place. The ocean is an engine, it runs on heat. When warm surface water, typically anywhere above roughly 80 degrees Fahrenheit, meets the right atmospheric conditions, low wind shear, high humidity, a pre-existing area of disturbed weather, it begins transferring enormous amounts of energy into the atmosphere. Water evaporates, rises, and condenses into clouds. That condensation releases heat, which drives air upward even faster, which pulls more warm, moist air in from the surface below. A feedback loop begins. The system starts to rotate because of the spin of the Earth itself. Pressure at the centre drops. Winds accelerate. A tropical storm is born. Given enough time and enough warm water, that system can become a hurricane or typhoon, with wind speeds exceeding 100, 150, even 200 miles per hour. The storm becomes a self-sustaining heat engine, feeding on the ocean below it and unleashing that energy as rain, wind, and devastation. That is a single storm. That is the system scientists have spent decades learning to predict. What happens when you have two of them running simultaneously in the same basin, close enough to influence each other? That is something else entirely. The phenomenon has a name. It's called the Fujiwara effect, named after a Japanese meteorologist who first described it more than a century ago. When two rotating storms come within a certain distance of each other, they begin to interact. They can orbit each other like two dancers locked in a slow, strange waltz. They can merge into a single massive system. One can absorb the other entirely, or they can deflect each other onto completely unpredictable paths. The problem is that all of those outcomes are possible, and right now the models disagree about which one is going to happen. That uncertainty is not a small thing. It is the difference between a catastrophic landfall hitting a densely populated coastline and a storm that recurves out to sea and spares millions of people. It is the difference between flooding that kills hundreds and flooding that kills thousands. The margin for error in storm forecasting is usually measured in miles and hours. Right now, it is being measured in hundreds of miles and days, and every hour the models stay in disagreement is another hour that emergency managers cannot issue the evacuation orders that might save lives. Let's talk about the two storms themselves, because each one, on its own, would already be a major story. The first system formed in warm, open water and rapidly intensified. That's the technical phrase forecasters use, and it's one that makes them nervous every time they say it. Rapid intensification means that a storm's maximum sustained winds increase by at least 35 miles per hour within a 24-hour period. It's a sign that all the conditions are perfectly aligned for a storm to explode in strength, and that is exactly what happened here. Within 48 hours of the first advisories, this system had gone from a disorganized cluster of thunderstorms to a powerful, well-organized hurricane with a clear eye visible on satellite imagery. The eye is significant. It means the storm has reached a level of organization where the center has cleared out, with air sinking down through the middle even as it rises in a furious ring of thunderstorms around the outside. A storm with a clear, defined eye is a storm that has figured out how to sustain itself. It's a storm that knows what it's doing. This first system, moving on a track that brought it across an expanse of extraordinarily warm water, continued to intensify. Sea surface temperatures along its path were running several degrees above the historical average for this time of year. That extra warmth is fuel, and this storm was burning through it. The second system developed several days later, but in a different part of the same ocean basin. Meteorologists had been watching a disturbance that had been churning for nearly a week without organizing. Then something changed. The upper-level winds that had been shredding the system and preventing it from developing suddenly relaxed. The environmental conditions shifted almost overnight. Within 36 hours, the second storm had organized, intensified, and earned a name of its own. Two named systems, both powerful, both tracking in directions that, on the maps, looked like they were going to converge. That's when the phone calls started. Senior forecasters began pulling together for emergency briefings. Satellite data was being ingested in real time. Aircraft reconnaissance planes were being sent directly into both storms to measure pressure, wind speed, and structure at multiple altitudes. The data they were sending back was confirming what the satellites were already suggesting. Both storms were strong, both were moving, and the interaction between them was already beginning. You can actually see it in the satellite loops if you know what to look for. The outer bands of the two storms, the tendrils of cloud that spiral outward from each system's center, were starting to reach toward each other. The circulation of one was beginning to distort the shape of the other. Two massive atmospheric vortexes, each one large enough to cover hundreds of thousands of square miles, were beginning to feel each other's presence. This is the moment in every major storm event when forecasters feel the ground shift under them. Because everything they've trained for, every model they trust, every statistical relationship they rely on, it was all built around understanding single storms in relative isolation. The double system interaction problem is one of the genuinely hard problems in atmospheric science. Not because scientists don't understand the physics, they do, but because the interaction is so sensitive to initial conditions that tiny differences in the measurements of each storm produce wildly different forecasts. Think of it this way. Imagine trying to predict exactly where two billiard balls will end up after a collision. If you know their exact speed and exact direction, you can calculate it. But if you're even slightly wrong about the speed of one ball, by a fraction of a percent, your prediction of where both balls end up can be off by a significant amount. The atmosphere is like that. Except the balls are the size of small countries and everything around them is also in motion. This is why the ensemble models, the approach where forecasters run dozens of slightly different versions of the same simulation to see the range of possible outcomes, were producing a spread of tracks that was alarming to look at. In a normal forecast, the ensemble members cluster together reasonably well. The spaghetti plots, as meteorologists call them informally, look like a loose bundle of lines all heading roughly the same direction. In this case, the spaghetti plot looked like someone had dropped the entire box of pasta on the floor. Tracks heading in every direction, some showing the storms merging, some showing them deflecting widely away from each other, some showing partial mergers, some showing one storm completely absorbing the other in a matter of hours. Every one of those scenarios has a completely different human consequence. Let's take them one by one, because understanding what each outcome would mean is essential to understanding why this event is being treated as a potential catastrophe. In the merger scenario, two storm systems combine into a single entity. The resulting storm would have access to the combined energy and organization of both systems. It would not necessarily be twice as strong. Storm systems don't add up that simply, but it could produce a larger, more expansive storm with a wider area of destructive winds and an enormous rain shield. A merged storm can also be harder to predict because its structure is different from a typical single storm. The eye wall, the ring of the most intense thunderstorms around the center, can become irregular and disorganized before reorganizing in a new configuration. That reorganization can sometimes lead to rapid intensification all over again. In the deflection scenario, the storms push each other off their expected tracks without fully merging. This is the scenario that emergency managers find most difficult to respond to. A storm that was expected to track north suddenly curves west. A system that computer models were placing well offshore suddenly has a more direct angle toward the coast. The deflection can happen quickly, in a matter of hours, and the change in track can be significant enough that evacuation routes and shelter plans built around one expected landfall location suddenly need to be reconsidered for a completely different coastline. And in the absorption scenario, one storm essentially consumes the other. This usually happens when one system is significantly stronger than the other, allowing the dominant storm to pull the weaker system's circulation into itself. the resulting storm can undergo a brief disruption as it processes the absorbed system, but then it can re-intensify, sometimes sharply. The energy that was in two storms is now concentrated in one. The rain bands that were distributed across a large area become focused. The wind field tightens and strengthens. Any of these outcomes could be catastrophic. None of them is a safe outcome, and right now the models cannot reliably tell us which one will happen. There is another layer to this story that goes beyond the immediate weather event. A layer that atmospheric scientists have been building the case for over many years, quietly, in journals and conferences that most people never read, and that has now become impossible to ignore. The ocean is warmer than it has ever been in recorded history, not warmer than it was 10 years ago or 30 years ago. Warmer than at any point since humans began systematically measuring ocean temperatures. The thermal energy available to fuel tropical cyclones across every ocean basin on Earth has increased substantially, and the effects of that increase are being felt in the statistics that describe how storms behave. Rapid intensification events, the kind that turned both of these storms from disorganized disturbances into major systems in days rather than weeks, are becoming more common. The percentage of storms that reach the highest intensity categories before making landfall has increased. The amount of rainfall that intense tropical cyclones produce has increased because a warmer atmosphere holds more water vapor, and a more intense storm sweeps up and deposits more of it. The area over which warm water, the fuel, is available for storm development has expanded poleward, meaning storms are forming and intensifying at latitudes that historically were considered too cool for major tropical activity. None of this means that every storm is now a monster. Natural variability is still a powerful force, but it does mean that when conditions align for a major storm event, the upper limit of what that event can become has shifted, the ceiling has risen, and in a system as non-linear as the atmosphere, pushing toward that ceiling can produce outcomes that are genuinely unprecedented. The double monster storm scenario currently unfolding is not something that can be blamed entirely on any single factor. The Fujiwara effect has been observed throughout meteorological history, but the fact that both of the interacting systems reach their current intensities so quickly, feeding on water temperatures that are historically anomalous, adds a dimension to this event that gives forecasters additional reason for concern, because it's not just the interaction that's unpredictable, it's the starting point of that interaction. Both storms entering this dance are stronger than they would have been in a cooler ocean. Whatever comes out the other side of the interaction, merger, deflection, absorption, it will be emerging from a starting point of exceptional intensity. While meteorologists work through the forecast uncertainty, on the ground in the potentially affected areas, emergency managers are doing something very difficult. They are preparing for multiple outcomes simultaneously. In a normal storm approach, emergency management follows a fairly clear script. A storm is tracked, a likely landfall zone is identified, evacuation orders are issued for vulnerable coastal areas, shelters are opened, supplies are pre-positioned. The system works, as imperfectly but functionally, because the forecast cone, the area within which the storm center is likely to travel, is small enough to focus resources. Right now, the cone is not small. The range of plausible tracks from the ensemble models covers an enormous stretch of coastline and interior terrain. Emergency managers cannot evacuate everywhere. They cannot pre-position enough supplies to cover every possible impact zone. They have to make decisions under uncertainty, betting on the most likely scenarios while trying not to leave entire populations unprotected if the unlikely scenario materializes. Those decisions are being made right now, in real time, in government offices and emergency operations centers, by people who are looking at forecast uncertainty that is genuinely wider than anything they typically work with. The psychological weight of that uncertainty should not be underestimated. Forecasters are trained to communicate confidence. They issue probabilities and forecast cones and impact graphics because those tools help the public understand risk. But there is a tension in meteorology between being precise, giving people actionable information, and being honest, acknowledging that in this case, the range of outcomes is exceptionally wide. Right now, the honest answer is that the atmosphere is doing something genuinely hard to predict, and the consequences of being wrong about it are measured in human lives. That is not a comfortable thing to say. But it is the truth. There is also the question of what happens after the storms make landfall or recurve away from populated areas. The immediate wind and storm surge threat is what drives evacuation orders, and gets the most attention. But the flooding threat from intense tropical rainfall is often the deadliest part of these events, and it extends far inland, far beyond the coastlines where the most dramatic damage occurs. A large, energetic tropical system can dump feet of rain over inland terrain in a matter of days. When two such systems interact and then one or both move inland, the rainfall totals can be extraordinary. Watersheds become overwhelmed. Rivers that normally take weeks to reach flood stage rise in hours. Communities that have never thought of themselves as being in a flood-prone area suddenly find themselves underwater. In recent years, catastrophic inland flooding from tropical systems has killed more people in some events than the coastal storm surge and winds combined. The rainfall forecast for this event is another area of significant uncertainty. The track uncertainty feeds directly into uncertainty about where the heaviest rainfall will fall. A slight wobble in the storm's ultimate path can shift the bullseye of extreme rainfall by 100 miles. That 100 miles can be the difference between a watershed that can handle the load and one that catastrophically fails. Reservoir managers, river forecast centres, dam safety officials and flood control agencies are all watching the same uncertain forecast maps that the meteorologists are watching, and they are making the same impossible decisions about when to pre-release water from reservoirs, when to issue flood watches and warnings, and when to tell people in inland valleys that it's time to move to higher ground. Historically, some of the deadliest storm disasters in recorded history have come not from the storms that everyone was watching, but from the storms that shifted direction at the last minute, intensified unexpectedly, or produced rainfall totals that exceeded every forecast. Those are the events that are seared into the memory of meteorology as a profession. The times when the atmosphere produced something that the models didn't fully anticipate, and people died as a result. Every forecaster working this event knows that history. They are trying very hard to make sure it doesn't repeat. There are tools available today that didn't exist a generation ago. Satellite technology has advanced to the point where forecasters can measure sea surface temperature, storm structure, wind speed, and the detailed internal architecture of a tropical cyclone with a precision that was unimaginable 50 years ago. Aircraft reconnaissance provides in-situ measurements directly inside the storms, sampling temperature, pressure, humidity, and wind at multiple altitudes. Numerical weather prediction models run on some of the most powerful supercomputers in the world, ingesting all of that data and producing forecasts that, on average, are far better than the forecasts of any previous era. And yet, the atmosphere does not bend to our tools. It operates on its own terms, according to physics that we understand in principle, but cannot perfectly simulate in practice. The Fujiwara interaction problem is a reminder that even with all of our technological sophistication, there remain scenarios in which the range of possible outcomes stays stubbornly wide until events force the uncertainty to collapse. The uncertainty will collapse. It always does. In the next 24 to 48 hours, as the two systems continue their interaction, one of the scenarios will begin to clearly dominate. The ensemble members will start to cluster. The spaghetti plot will tighten up. Forecasters will be able to issue more confident guidance about tracks and intensity, and emergency managers will be able to make more targeted decisions about where to focus resources. But that window of collapsing uncertainty is also the window of maximum danger for people in the path of these storms. Every hour that passes is an hour closer to landfall or to the most intense phase of the interaction. Every hour the forecast stays uncertain is an hour that people who might need to evacuate are still waiting for clearer guidance. The frustrating reality of storms like this is that certainty and safety often move in opposite directions. By the time we know exactly where the storm is going, it may be too late to move everyone who needs to move. This is why the current event has triggered the level of concern that it has, not just because two powerful storms are interacting in an unusual way, not just because the ocean fueling them is warmer than historical records have ever shown, but because the combination of those factors is producing a situation where the tools that emergency managers rely on to protect people are operating at the edge of their capability, at exactly the moment when the stakes are highest. The scientists watching the satellite feeds, running the models, and flying into the storms are doing everything that can be done with the knowledge and technology that exists. They are working the problem with extraordinary skill and dedication, and they are terrified, not because they don't understand what's happening, but because they understand it well enough to know how serious it is. The atmosphere is sending a message right now that is written in warm water and spiraling cloud bands and pressure gradients that span hundreds of miles. The message is that the Earth's weather system is operating at an intensity that is pushing the boundaries of what our modern forecasting infrastructure was designed to handle. For the people in the path of these storms, whether that path ultimately curves through a densely populated coastline or bends out to sea at the last moment, the next several days will be defined by decisions made under uncertainty. By emergency managers who cannot wait for perfect information, by families who have to decide whether to leave or shelter in place before the forecast is fully resolved, by meteorologists who are doing their best to translate a chaotic and rapidly evolving atmospheric situation into guidance that is both honest and actionable. The storms are real. The interaction between them is real. The fear in the voices of people who have spent their careers studying these systems is real. And the outcome, wherever it falls on the wide spectrum of possibilities that the models are currently showing, will be real in ways that numbers on a screen cannot fully convey. What happens in the next 48 hours will be studied for years. It will shape how forecasters communicate uncertainty and future events. It will inform how emergency managers prepare for scenarios in which two major systems interact simultaneously. It will add a data point to the growing record of extreme weather events that are forcing atmospheric scientists to rethink what the upper boundary of tropical storm behavior actually looks like in a warming world. But all of that analysis comes later. Right now, the storms are still out there. They are still interacting. They are still feeding on water that is warmer than it has ever been. And the people who watch them for a living are watching very, very closely by hoping that the atmosphere chooses one of the less catastrophic paths through the chaos it has created. That hope is real. The danger is real. And anyone who lives in a potentially affected area, who has family or friends in the impact zone, who looks at those swirling clouds on a satellite loop and feels something tighten in their chest, they are right to feel it. The forecasters are terrified because they know what these systems are capable of. And right now, with two of them locked in an unpredictable atmospheric waltz over warm open water, the full range of that capability is still, agonizingly, in play. The watch center that is coordinating the response to these two storms is not a glamorous place. It's a room full of screens, most of them covered in data that would look like noise to anyone who hadn't spent years learning to read it. There are coffee cups everywhere. There are people who have not slept in 36 hours staring at trajectory plots and trying to will the ensemble members to cluster. If you walked in off the street, you would probably not feel the gravity of the situation from the room's appearance. You would feel it from the silence. The particular quality of silence that settles over a group of people who are all thinking very hard about the same very bad thing. The forecasters in that room are the product of a system that was built, largely, in response to disasters. The modern National Hurricane Center as a formal institution grew out of the recognition that storms were killing people who could have been warned. The networks of observations, the aircraft reconnaissance program, the numerical modeling infrastructure, the public communication systems, all of it was developed, piece by piece, in the wake of catastrophes that revealed the inadequacy of what existed before. Every major advancement in the way we track and predict tropical cyclones has a tragedy somewhere in its lineage, a death toll that motivated someone to build something better. That history matters right now because it means the people in that room are not naive about what failure looks like. They have read the case studies. Some of them were there for previous events where the forecast broke down at the worst possible moment. They know what it looks like when a storm does something the models didn't anticipate, and they know what the human cost of that looks like in the aftermath. That knowledge is not paralyzing. These are professionals, and they keep doing their jobs, but it is present in the room, a kind of institutional memory that keeps everyone focused and no one casual about the work. One of the things that has changed in recent years, and that matters enormously in an event like this one, is the relationship between the forecasting community and the emergency management community. For much of the history of hurricane meteorology, those two groups operated in relative isolation. The meteorologists made forecasts, they issued advisories, and they handed those off to emergency managers, who then decided what to do with them. The cultures were different, the languages were different, the time horizons were different. Meteorologists think in hours and days. Emergency managers think in the time it takes to move large numbers of people across road networks that weren't designed for simultaneous mass movement. Over the past 2 decades, a sustained effort has been made to integrate those communities more closely. Joint exercises, shared training, regular communication about how forecast information is being used and misused. Emergency managers have gotten much better at reading probabilistic forecast products, the tools that express uncertainty rather than just giving a single track and intensity. Meteorologists have gotten much better at thinking about the decision timelines that emergency managers are working against. That integration is being tested right now, because the forecast uncertainty is wide enough that the normal communication frameworks are straining under the load. When you can't tell an emergency manager whether the major landfall is going to be in one state or in an entirely different state 300 miles away, the tools that were designed for the normal range of forecast uncertainty are not sufficient. The conversations happening right now between the forecast office and emergency management agencies are not following a script. They are genuinely novel. People are asking questions that don't have established answers. How do you issue a hurricane watch for a coastline that spans multiple states when you genuinely don't know which part of it is going to be hit? How do you sequence evacuations when the storm track could shift the critical zone by hundreds of miles in either direction within the next 24 hours? How do you communicate that kind of uncertainty to a public that has been trained to look for a cone and plan around it? The communication problem deserves its own careful attention because it is not separate from the meteorological problem. It is part of it. A forecast that is technically correct about the range of possible outcomes but fails to motivate the right protective actions from the right people at the right time is, in the most important practical sense, a failure. The whole point of the forecast is to save lives. If people in a high-risk area stay put because the uncertain forecast didn't sound urgent enough, and then the storm hits that area at full strength, the meteorological accuracy of the forecast is cold comfort. This has actually been one of the more complicated and contentious debates inside weather communication over the past decade. The traditional forecast cone, that cone-shaped graphic showing where the storm center is likely to travel, was designed to communicate track uncertainty. It does that reasonably well, but it communicates almost nothing about intensity, and it communicates very little about the spatial extent of dangerous conditions, which can stretch hundreds of miles from the storm center. People who live outside the cone but within the area of tropical storm or hurricane force winds, who are still in genuine danger, often interpret their location outside the cone as meaning they're safe. They're not. There have been repeated proposals in the forecasting community to retire the cone graphic, or replace it with something that more accurately represents the full risk picture. Those proposals have met with significant resistance, not because meteorologists disagree about the cone's limitations, but because changing a tool that has been used for decades risks creating confusion during exactly the moments when clarity is most needed. The devil you know problem, applied to public communication during emergencies. Now add to that familiar tension the specific challenge of this event, where two storms are interacting and the track uncertainty is far wider than what the cone was designed to represent, and you have a communication challenge that the existing toolkit is genuinely not equipped for. The forecasters know this. The emergency managers know this. They're improvising in the most professional and high-stakes sense of that word. They're reaching for language and frameworks that can convey the real situation to a public that is trying to make decisions about whether to stay or go, and they're doing it under time pressure with incomplete information in a situation that has no clear precedent in recent memory. What they keep coming back to is a version of the same message. The uncertainty about exactly where and when is high, but the certainty about the severity of the threat is not. Both of these storms are serious systems. The interaction between them creates risk across a very wide area. If you are in a potentially affected region, you should not wait for the forecast to narrow before you begin preparing. The window for safe preparation is closing faster than the forecast uncertainty is resolving. That message is the right one. Whether it will be heard by enough people, and whether it will be heard soon enough, is the question that no one in the forecast center can answer. That part is outside their control. Let's step back from the immediate emergency for a moment, because there is a deeper story running underneath this event that connects to something much larger than two storms over a warm ocean. The warming of the world's oceans is not an abstraction. It is a physical fact that is measurable, that has been measured with increasing precision for decades, and that is now manifesting in the behavior of tropical cyclones in ways that are visible in the data. For most of the 20th century, the study of climate change and the study of hurricanes were largely separate disciplines. Climate scientists worried about long-term trends. Hurricane scientists worried about the next storm. The two communities occasionally spoke at conferences but operated on different timescales and with different methodologies. There was a reasonable argument that individual weather events and long-term climate trends were essentially independent questions. That argument has become very difficult to sustain, not because scientists have abandoned their commitment to distinguishing weather from climate. That distinction is still valid and important, but because the trends in the climate system are now large enough and fast enough that they are visibly altering the context in which individual weather events occur. The ocean temperature anomalies that helped rapidly intensify both of these storms are not noise. They are a signal, and that signal is growing. The science on this has moved significantly in the last 10 years. Early studies on the relationship between warming and hurricane intensity were cautious, appropriately so given the complexity of the system and the relative shortness of the reliable observational record. But as the satellite era has lengthened and the observational datasets have grown, the patterns have become clearer. Storms are intensifying more rapidly. The most intense storms are getting more intense. The proportion of storms that reach the highest categories before landfall has increased. Rainfall rates from tropical systems have increased measurably, consistent with the physical expectation that a warmer atmosphere carries more water vapor. None of this means that any individual storm is simply a product of climate change. The Fujiwara effect is not caused by warming. Tropical storms have always formed and intensified in warm water. The natural variability of the climate system has always produced periods of heightened hurricane activity and periods of relative calm. But the background state against which all of that natural variability plays out has shifted. The warm water that feeds these storms is warmer, on average, than it used to be. That extra warmth raises the ceiling on what any given storm can become, and when natural variability and background warming align, as they appear to be doing right now, the results can push toward the upper range of what the atmosphere is capable of. There is a concept in statistics called stacking the deck. If you change the probability of certain outcomes even slightly, and you run enough trials, the results start to diverge significantly from what the baseline probability would predict. Weather events are like that. You don't need to change the probability of a major hurricane by a lot to see a meaningful increase in the number of major hurricanes over decades. You don't need to dramatically increase the rainfall intensity of each event to produce outcomes that exceed what flood infrastructure was designed to handle. What atmospheric scientists are watching right now is the accumulation of small changes that individually seem incremental, but collectively represent a significant shift in the behavior of the climate system. The double storm event over warming oceans is one particularly dramatic manifestation of that shift, but it's not the only one. Over the past several years, forecasters and climate scientists have been grappling with a cluster of phenomena that each, on its own, might be explicable through natural variability, but that taken together suggest something more systematic is happening. Storms are maintaining their intensity for longer after landfall because the inland areas they move over contain more moisture in the air and warmer surface temperatures. The seasonal window during which tropical cyclones can form has lengthened at both ends, earlier in spring, later in fall, as warm water persists for longer periods. The latitudinal range over which storms can maintain hurricane-force winds has expanded, with systems reaching unusual intensities in regions where major tropical storms were historically rare. Each of these observations carries its own uncertainty. The observational record for the details of tropical cyclone behavior, particularly at regional and seasonal scales, is not long enough and is not consistent enough in its methods to draw firm statistical conclusions about every trend. Climate scientists are careful about this. They resist overstating what the data shows, and they are equally resistant to understating it. The honest answer is that the physical theory predicts these changes, the available data is consistent with the predictions, and the uncertainty about the magnitude and pace of the changes is being progressively reduced as the record grows. What the honest answer does not allow for is comfortable inaction. The uncertainty runs in both directions. The changes might be less severe than the central projections suggest. They might also be more severe. The physics that governs the relationship between ocean temperature and storm intensity doesn't have a built-in limit at the level that historical observation happens to describe. If you keep warming the ocean, you keep increasing the potential energy available to storms. How much of that potential energy gets realized in any given storm is still partly a matter of atmospheric dynamics and natural variability. But the potential itself, the reservoir of energy that storms can tap, is filling up. Meanwhile, the coastlines that these storms threaten have not stood still. Over the same decades during which ocean temperatures have been rising, human populations on coastlines around the world have grown substantially. Low-lying coastal areas that were largely uninhabited or lightly populated in the middle of the 20th century are now densely developed. Beachfront real estate has been built out. Infrastructure, roads, bridges, water systems, power grids has been extended into areas that storm surge can reach. At the same time, many of the natural features that historically provided some degree of protection against storm surge and coastal flooding have been degraded. Mangrove forests, which are extraordinarily effective at absorbing wave energy and slowing storm surge, have been cleared for development across large stretches of tropical and subtropical coastline. Coastal wetlands and barrier islands, which act as natural sponges and buffers, have been drained, built over, or eroded faster than natural processes can replace them. Coral reefs, which dissipate wave energy before it reaches shorelines, are under severe stress from warming and acidifying oceans. The result is a compounding risk. More intense storms meeting less protected coastlines with larger populations in their paths. The risk of catastrophic outcomes from major tropical cyclone events has grown not from one factor, but from several, all moving in the same direction at the same time. This is the context in which emergency managers in the affected regions are doing their work right now. They are not just dealing with two powerful storms, they are operating within a risk landscape that has changed significantly from the risk landscape that the infrastructure they're managing was built to handle. The evacuation routes were designed for traffic volumes that may or may not be sufficient for current population levels. The storm surge maps that define evacuation zones were built on historical storm climatology that may no longer accurately represent the storms that can actually arrive. The building codes that govern what structures people are sheltering in were written around wind speeds and flooding levels that may have been exceeded by what these storms are capable of. None of this means that the emergency management community is helpless or unprepared. These are, on the whole, very capable organisations staffed by dedicated people who work hard at a genuinely difficult job. But it does mean that the margin for error is thinner than the official infrastructure might suggest. And in an event where the forecast uncertainty is as high as it is right now, that thin margin is being asked to carry a very heavy load. The aircraft flying into the storms right now are doing something that deserves more attention than it typically gets outside of the meteorological community. Hurricane Hunter aircraft, specifically modified to fly through conditions that would destroy a commercial plane, are the primary source of direct in-storm measurements that the numerical models use to pin down the current state of each system. The satellites can tell you a great deal about a storm's structure and intensity from the outside. The reconnaissance aircraft can tell you what's actually happening at the core. Flying into a hurricane or typhoon is exactly as violent as you would imagine, and probably worse. The updrafts and downdrafts inside a major tropical cyclone's eyewall are strong enough to slam aircraft against their seat restraints, with forces that test the structural limits of the airframe. Instruments sometimes fail in the turbulence. The crews who do this work are trained specifically for these conditions, but the conditions are not and cannot be routine. What the aircraft are measuring in these two storms right now is being fed directly into the forecast models with minimal delay. The measurements being taken as the planes penetrate the eyewalls and sample the inner core of each system are the most valuable single inputs into the forecasts. The central pressure measurements, the barometric pressure at the storm's core, are the best available real-time proxy for a storm's intensity, better than satellite estimates, better than radar. When a reconnaissance aircraft reports that the central pressure in one of these storms has dropped by several millibars in the span of a few hours, that is an unambiguous signal that the storm is intensifying, and it triggers immediate updates to the forecast. The data from the current reconnaissance missions is showing something that is not exactly reassuring. Both storms remain highly organised. Both are maintaining the kind of structural integrity that characterises long-lived, deeply energised systems. The interaction between them has not yet disrupted either storm's inner core in the way that sometimes happens in the early stages of Fujiwara encounters. That means the interaction so far has been more of an orbital dance than a disruptive collision, which actually increases the uncertainty about how it ultimately resolves. A Fujiwara interaction that quickly disrupts one or both storms tends to resolve faster, though not necessarily more safely. An interaction where both storms maintain their internal organization for longer can produce a more prolonged period of uncertainty, because both systems remain potent actors in the atmospheric drama, and neither one is being weakened by the interaction itself. What is happening right now is closer to the latter. Two well-organized, energy-rich systems, each aware of the other's presence in the atmospheric sense, circling, influencing each other's tracks without yet decisively merging or deflecting. The models, as mentioned, are still disagreeing about how this resolves, but there is an important distinction to draw in how the model disagreement is structured. Early in the forecast period, the disagreement was about fundamental outcomes, merger versus deflection versus absorption. Now, as more data has come in and more of the interaction has played out, the range of outcomes is narrowing slightly, but in a way that is not straightforwardly reassuring. The scenarios in which the interaction is relatively benign, where both storms quickly deflect away from populated areas, have become somewhat less probable in the latest ensemble runs. The scenarios that involve at least one system making significant landfall have become more prominent. This is the part of the forecast evolution that forecasters watch most anxiously. When the narrowing of uncertainty moves toward the worse outcomes rather than the better ones, when the models begin to agree not that the storms will spare the coast, but that at least one of them will not, the urgency in the watch center changes register. The public communication that accompanies forecast updates at this stage is carefully crafted and also, inevitably, insufficient. There is simply no way to fully convey in a 60-second broadcast segment or a social media post the combination of scientific complexity, genuine uncertainty, and serious risk that this event represents. The official products, the track forecasts, the wind speed probabilities, the storm surge maps are the best available tools, and they are genuinely useful. But they require interpretation, and they require a level of engagement with probabilistic information that many people, through no fault of their own, have not been trained to provide. The gap between what the forecasters know about the risk and what the public understands about the risk is one of the persistent challenges in emergency meteorology. It's a gap that exists in normal storm events and widens substantially in events like this one, where the technical complexity of the situation defies easy summary. Forecasters do their best to bridge it. They choose words carefully. They work with meteorologists who specialize in communication to craft messages that are both honest and actionable. They engage with local emergency managers who can translate national forecast products into specific guidance for specific communities. But the gap never fully closes, and in the moments when it matters most, or when people who need to decide whether to leave are trying to interpret what the storm track uncertainty means for their specific neighborhood, the gap can cost lives. This brings us to something that forecasters have known for a long time and that researchers in risk communication have been trying to solve for decades. The problem is not just about information, it's about trust. It's about the relationship between the people who issue the warnings and the people who receive them. And that relationship is built, or damaged, by every interaction that precedes the critical moment. When a community has experienced a storm forecast that turned out to be overstated, when an evacuation was called and the storm turned or weakened before making landfall, there is a cost to that experience that shows up in the next event. People remember. They remember the gas they spent and the money they lost and the hassle they went through, and the storm never came. And the next time the watch center issues an urgent warning, some of those people discount it. Not out of irrationality, but out of a perfectly reasonable updating of their personal probability assessment based on prior experience. This is the cry-wolf problem in emergency meteorology, and it is taken very seriously by the forecasting community. A false alarm is not cost-free. Every time a storm forecast proves worse than the outcome, it erodes a fraction of the credibility that the next forecast will need. Over many events and many communities, those fractions add up. The result is populations in high-risk areas that are systematically less responsive to warnings than the risk warrants. The challenge is that there is no clean solution. Forecasters cannot narrow their warnings to only the events they are completely certain about, because the nature of uncertainty means that some of the most dangerous events are precisely the ones that look uncertain until very late in the forecast period. The double storm event currently unfolding is a perfect example. A forecaster who decided to wait for the models to resolve before issuing strong guidance would be making people safer from false alarms, while potentially making them less safe from the actual event. The calibration of this tension is one of the most difficult professional judgments in meteorology. Different forecasters and different forecast offices have developed different philosophies about where to set the threshold. Research on how people respond to warning messages under uncertainty has produced a set of guidelines and best practices, but they are guidelines, not algorithms. The final call is still made by human beings who are weighing probabilistic information against their understanding of how populations respond and their assessment of what the atmosphere is doing. Right now, those human beings are leaning toward urgency. They are leaning toward explicit acknowledgement of the extraordinary nature of this event. They are collectively reaching for language that conveys both the genuine uncertainty and the genuine danger in a way that motivates protective action, without pretending to certainty they don't have. How that message lands, whether it reaches the people who need it, whether it produces the behavior that saves lives, that is happening in real time, in millions of individual conversations and decisions, in communities that span a huge swath of potentially affected geography. The history of major storm disasters includes a subset of events that are particularly painful to study, because they are the events where the warning system worked as well as it could, and people were still killed. Not because they ignored the warnings, but because the warnings came too late, or because the path to safety was blocked, or because the storm behaved in a way that the forecast didn't capture well enough to allow adequate preparation. These are the events that haunt the meteorological community most persistently, not the cases where a forecast was wrong and people died because they trusted it and went the wrong way. But the cases where everything was done right, up to the point where everything done right was still not enough. Those events illuminate the limits of what warning systems can accomplish, even when they function optimally. They highlight the importance of the non-meteorological parts of the disaster resilience picture: the physical infrastructure, the social support systems, the economic capacity of communities to prepare and recover, the political decisions that shape where people live and what protections they have. A warning that tells people to evacuate is only as effective as the system that makes evacuation possible. In a community with inadequate transportation infrastructure, with large numbers of people who lack the economic resources to stay somewhere else during an evacuation, with a history of structural underinvestment in emergency preparedness, in that community, a perfect forecast still cannot guarantee adequate protection. This is a difficult thing to say in the context of an ongoing event, because it can sound like an excuse or a deflection from the immediate task at hand. It is not intended that way. The immediate task is vitally important, and the people doing it are working as hard as they can. But the immediate task sits within a larger system, and the limits of what the immediate task can accomplish are real, and they are shaped by choices that have been made over years and decades by communities and governments about how to allocate risk, invest in infrastructure, and protect the most vulnerable people. The communities that will be most at risk if one or both of these storms makes major landfall are not uniformly at risk. Within any affected area, there are neighborhoods and populations whose risk is qualitatively different from others. Mobile homes and manufactured housing fail in tropical storm-force winds that newer concrete construction can survive. Low-income neighborhoods are more likely to be sited in flood-prone areas, partly as a legacy of historical patterns of development and discriminatory zoning. Elderly populations and people with mobility limitations face particular challenges in evacuating. Communities where English is not the primary language face additional barriers to receiving and acting on official warning information. Emergency managers know all of this. The best ones build their plans around it, working specifically with the organizations and community leaders who have access to the most vulnerable populations. But the resources available for this kind of targeted outreach are rarely equal to the scale of the need, and in an event where the forecast uncertainty is unusually high and the potentially affected area is unusually large, the capacity to reach every community that might be in danger is strained severely. The next 12 to 24 hours will be a period of accelerating decisions. The forecast uncertainty is still wide, but it is narrowing, and as it narrows, the window for certain protective actions is closing. Evacuating a coastal community with a large population, including hospitals, nursing homes, and correctional facilities, takes time that is measured in days. Some of that time has already been used. The decisions about which communities to evacuate and when are being made right now, under the weight of forecast uncertainty that hasn't fully resolved. There is a phrase that experienced emergency managers use that captures something important about how these decisions get made. They talk about protecting against regret, not optimizing outcomes, not maximizing expected utility, not playing the probabilities in the strict sense, protecting against regret, specifically protecting against the regret of having waited for more information when more information didn't come in time and people died as a result. It's a human way of making decisions, and it doesn't always produce the technically optimal outcome. Sometimes protecting against regret means evacuating an area that the storm ultimately doesn't hit, and that costs money and causes disruption and erodes future compliance. But in the cases where the storm does come, where the decision to wait would have cost lives, protecting against regret is the right framework. It is the framework that matches the asymmetry of outcomes. The cost of unnecessary evacuation, while real, is recoverable. The cost of insufficient evacuation, when a major storm hits an unprepared population, is not. The forecasters and emergency managers coordinating this response are all working within some version of this framework right now. They are making decisions that may prove to be unnecessary, and they are doing so deliberately, because the alternative, waiting for certainty that may not arrive before it's too late to act, is worse. Understanding this framework is important for anyone who lives in a potentially affected area and is trying to decide what to do. The uncertainty in the official forecast is not a reason to wait. It is a reason to act sooner, not later. Because the direction in which the uncertainty is likely to resolve, toward more confidence about the storm's track and intensity, arriving as the storm is already close to the coast, is not a direction that gives you more time, it gives you less. If you are in an area that has been identified as potentially at risk, the fact that the forecast hasn't fully resolved is not information about your specific risk. Your specific risk may be very high, even if the exact track isn't pinned down. The range of scenarios that emergency managers are working against includes serious impacts across a very wide area. Being outside the current track forecast does not mean being safe. Being inside it does not mean certain disaster. The honest advice is to prepare, as if the worst case for your area is plausible, even if it's not the most likely. That is also essentially what the forecasters wish they could tell every person in the potentially affected zone. Not, here is exactly what will happen, but here is the range of what can happen, and across that range, protective action is warranted right now. There is something worth dwelling on about the specific nature of the fear that develops in a situation like this, the fear that the forecasters themselves are feeling. It is not quite like other kinds of fear. It is not the fear of someone standing in the storm, facing immediate physical danger. It is a more abstract and in some ways more exhausting kind of fear. The fear of watching something unfold from a distance, with partial information, knowing that the outcome matters enormously, and that what you can do to influence it is limited to the accuracy and clarity of the information you provide. Meteorologists, particularly those who work in operational forecasting, the people who issue the actual advisories that drive public action, live with a version of this fear as a professional constant. They are always, to some degree, in the position of knowing more about what might happen than the people whose lives depend on that knowledge, and less than what would be needed to be certain. In normal operations, the uncertainty is manageable. The forecast tools perform reliably within a reasonable range, and the gap between what they know and what they wish they knew is tolerable. In an event like this one, that gap opens up. The forecast tools are still performing. They're doing what they're designed to do, which is characterize the range of possible outcomes. But the range is wide and the stakes are high, and the knowledge that people are making life and death decisions based on your products that you know are carrying more uncertainty than usual, is not something that fades into the background when you're trying to think clearly about the next forecast cycle. There is a piece of the forecaster's emotional experience that is rarely described in public-facing coverage of these events: the period after. The period when the storm has made its choice, the models have verified or not verified, and the forecaster is sitting with the knowledge of how it turned out. The outcomes that haunt the forecasting community are not necessarily the ones where a bad forecast led to bad outcomes. Sometimes those are explainable, justifiable, understandable given what was known. The ones that stay with people are the ones where a small different choice in the forecast, a slightly different emphasis in the communication, might have changed what people did and whether they survived. That is a weight that the people watching these two storms right now are already carrying, before either system has made landfall, before the outcome is known. They are carrying it in anticipation, with the knowledge that within a few days they will know how it turned out, and they will be reviewing every decision they made along the way, asking whether it was right. Most of the time, it will be. Most of the time, the forecast was as good as the data allowed, the communication was as clear as the tools permitted, and the decisions were made according to sound professional judgment. Most of the time, that is enough. Sometimes, in ways that the professional community never fully accepts or dismisses, it isn't. And sitting in the watch centre right now with two powerful storms interacting over warm water and a public that is trying to figure out what to do, that knowledge is part of the atmosphere in the room, as surely as the data on the screens. Let's talk about what happens if the worst of the plausible scenarios materialises. Because one of the things that is important to understand about a major storm disaster is that the devastation is not evenly distributed in time. There is the acute phase, the wind and surge and rain during the storm's passage, and then there is the aftermath, which is sometimes more damaging in the aggregate, and which is almost always less visible to people who are not directly in it. A major storm landfall at Category 4 or 5 intensity, the kind that is within the range of what either or both of these storms could produce, generates a kind of destruction that is almost impossible to fully communicate through numbers alone. The storm surge, the wall of water that a major hurricane pushes ahead of it and drives inland, can be 15-20 feet high. It arrives with the force of moving water behind it, which is one of the most destructive forces in nature. A cubic yard of water weighs roughly 1,700 pounds. Storm surge doesn't just inundate structures, it destroys them, sweeping away concrete foundations and moving cars like toys and depositing boats in living rooms. The wind damage at major hurricane intensity is similarly comprehensive. Trees come down, power lines come down, roofs peel off structures that were built to code. Structures that were not built to code are sometimes simply gone. The debris that major wind events generate, pieces of building materials, signage, vegetation, becomes a secondary hazard that can kill even in areas where the direct wind effects are survivable. And then comes the rain. The rainfall from a slow-moving major tropical system can be measured in feet over a period of days. Infrastructure that was designed to move water, storm drains, culverts, river channels, is overwhelmed, often within hours. The flooding that results is not the same as coastal flooding. It spreads across the terrain wherever the water can flow, filling basements, rising in places that don't appear on any flood map, discovering weaknesses in roads and bridges and earthworks that decades of drier weather had never revealed. The recovery from this kind of damage is measured in months and years, not days and weeks. Power grids can take weeks to restore after major wind damage. Rebuilding housing stock takes years, particularly when the storm hits a large area, and the construction capacity of the affected region cannot meet the demand that the damage creates. Communities that experience major storm disasters often find that the population returns more slowly and less completely than anyone expected. Businesses close permanently because they can't afford to wait for the customer base to come back. People who left to stay with family during the evacuation find reasons not to return. The job that didn't survive the closure, the school district that's been disrupted, the house that needs months of work before it's habitable again. The economic data on major storm impacts tells a story that the immediate disaster coverage often misses. The sharp visible losses, the property damage, the insured losses are actually only part of the total economic cost. The longer-term effects, the disrupted livelihoods, the displaced businesses, the degraded infrastructure that takes years to fully rebuild, the public health consequences of prolonged displacement and damaged water systems, the mental health effects of trauma and uncertainty. These costs accumulate over a much longer period and often exceed the immediate physical damage in total. For the communities that are in the potential path of this event, that future is not abstract. It is what people are thinking about when they consider whether to stay or go, whether the house will be there when they come back, whether the job will still exist, whether the neighbourhood will look the same, whether the risk is worth it to stay and protect property that might not be protectable against what's coming. These are not irrational considerations. They are the actual lived calculus of people who are trying to make the best decision they can under conditions of genuine uncertainty and stakes that could not be more personal. The advice from emergency managers is, almost universally, to leave. Structures can be repaired, property can be replaced, at least partially. Lives cannot be recovered. The math strongly favours evacuation when a major storm is threatening. But the math assumes that evacuation is feasible, that people have the resources, the transportation, the destination, the support system to make leaving work. And for a significant fraction of the populations in storm-prone areas, that assumption is not fully justified. This is one of the structural inequities in how storm disasters play out. The populations that are most vulnerable to the physical effects of a major storm, those in low-lying coastal areas, in structurally inadequate housing, without the economic cushion to weather a prolonged displacement, are often also the populations for whom evacuation is most difficult. The evacuation order is an equalizer in theory but not in practice. The wealthy family with a car, a credit card, and a cousin in another state has options that a low-income family without transportation and with no social network outside the affected area does not. Emergency management agencies have improved their approach to this disparity over the years. Transportation assistance programs, special needs registries that track people who need help evacuating, partnerships with community organizations that have the trust of vulnerable populations. These tools exist and they help. But they are rarely fully funded and rarely fully utilized, and in an event where the potentially affected area is unusually large and the lead time is being compressed by forecast uncertainty, the gaps in those systems become more consequential. There is also the complicating factor of what happens when two storms mean that the typical mutual aid that states and regions provide to each other during storm recovery might be unavailable. When a major storm hits one state, neighbouring states typically send resources, personnel, and equipment to support recovery. When two major storms are simultaneously threatening a broad region, that mutual aid calculus becomes much more complicated. The neighbouring state that would normally send extra linemen and equipment to help restore power after a storm may be facing its own storm impacts and may have its own resources fully committed. This is not a hypothetical concern. The scenario where two active storm systems impact a region in relatively close succession, or simultaneously, if the Fujiwara interaction produces a landfall situation where one system's outer bands are affecting areas before the second system has cleared, creates a resource allocation problem that is genuinely different in kind from the normal single storm response. The logistics of deploying and coordinating recovery resources across a multi-storm, multi-impact zone scenario are substantially more complex than what the regional and national emergency management systems were designed around. Federal emergency management agencies have modelled multi-disaster scenarios and have developed contingency plans for exactly these situations. But modelling and reality are not the same thing, and the response to an actual simultaneous multi-disaster event would necessarily involve improvisation and real-time adaptation of plans that were built around scenarios that may not exactly match what's happening. The people in emergency operations centres thinking through this right now are asking hard questions. Where do you pre-position resources when you don't know which of two large areas is going to be harder hit? How do you sequence search and rescue operations if two storm systems are making landfall within days of each other in different parts of the same region? Who gets the first response? And how do you make that decision in a way that doesn't leave an entire community without support during its most critical window? These questions don't have algorithmic answers. They require judgment, coordination, and a degree of trust between the agencies and levels of government that are involved that has to be built over years and exercised before the crisis hits. Whether that trust and that coordination are adequate to what this event might demand is something that will only be fully answered in the aftermath. Now, there is an aspect of this story that involves a different kind of watching, the watching that happens not in a government forecast centre but in research institutions, in university atmospheric science departments, at the computer terminals of scientists who are not directly involved in the operational response, but who are tracking this event with intense professional interest, because of what it might tell them about how the atmosphere is behaving at the edge of the systems they study. For researchers in tropical meteorology and climate science, events like this one are, in the most clinically honest sense, scientifically valuable. Not in a way that anyone would celebrate given the human stakes, and the scientists involved are deeply aware of those stakes, but in the sense that extreme events contain information that normal events don't. The behaviour of two major tropical cyclones in close proximity interacting over a historically anomalous warm ocean during a period of exceptional atmospheric conditions is a natural experiment that will generate data that researchers will be analysing for years. What they are hoping to learn from this event goes beyond the immediate forecast question of what happens next. They want to understand the Fujiwara dynamics more precisely, because the observational record for close twin storm interactions at this intensity is thin. They want to understand how the anomalously warm ocean surface is influencing the energy budget of each storm, and whether the interaction dynamics are altered by that extra energy in ways that current theoretical frameworks predict. They want to understand whether the rapid intensification episodes that produce these two systems are consistent with what climate models project should happen as sea surface temperatures continue to rise, or whether there are dynamics at play that the models don't fully capture. This research interest is not separate from the operational problem. The operational models that forecasters use to predict track and intensity are built on the same physical understanding that researchers develop and refine. Better science about how Fujiwara interactions work feeds directly into better model parameterizations, which feeds directly into better forecasts in future events. Every major storm event generates post-analysis data that goes into improving the next generation of forecast tools. The scientific community's relationship with major storm disasters is genuinely complicated in this way. The researcher who is watching satellite imagery of two powerful storms interact over a warming ocean feels grief for the communities in their path, urgency about the science, and professional responsibility to extract every possible insight from what the atmosphere is showing, all simultaneously. That combination of feelings is not comfortable, but it is honest, and it is the combination that drives the incremental improvements in understanding that eventually, over many events and many years, translate into better forecasts and fewer preventable deaths. One thing that researchers are paying close attention to in this event is the behavior of the warm core structures of each storm, the thermal architecture of the upper atmosphere above each system's center. Tropical cyclones are, at their core, thermal engines. The warm air in the upper atmosphere above a hurricane's center, the so-called warm core that characterizes all tropical cyclone systems, is what defines them as tropical rather than extratropical. The intensity of that warm core, its vertical extent, and how it responds to the interaction with another system are all things that satellite instruments can measure with growing precision. The warm core structure of each of these systems has been well developed and robust throughout their intensification phases. That robustness is part of what has allowed both storms to reach their current intensities, despite the mild to moderate interaction already occurring between them. Typically, as two systems begin to interact, the disruption of the outer circulation can weaken the warm core somewhat. In this case, both cores remain intact, suggesting that the interaction has not yet penetrated to the heart of either system. What happens when the interaction does begin to affect the cores, and the geometry of the system strongly suggests that it will, is a key unknown. The most benign outcome is that the interaction disrupts both systems enough to prevent further intensification and begins the process of a partial merger that produces a weaker, less organized combined system. The least benign outcome is that the interaction reorganizes the energy of both systems into one, intensifying rather than weakening the result. Current physical understanding suggests the former is more probable, but the current physical understanding of how twin storm interactions evolve at these intensity levels has not been extensively validated against real observations. This is one of those situations where the honest scientific answer and the answer that would be most reassuring to hear are in direct conflict. The honest answer is that we don't know with precision, and the observations that would help us know better are the same observations that are being generated right now by this event. The reassuring answer would be that the models have this covered, that we've seen this before, and we know how it ends. The honest answer is better, even though it is harder. The satellite data coming in over the next several hours will start to constrain the uncertainty significantly. The reconnaissance aircraft are scheduled for additional penetrations of both cores, and the pressure measurements they return will tell forecasters whether the interaction has begun to affect the intensity of either system. Radar coverage, where available, will start to provide real-time information about precipitation structure and the evolving rain band geometry around each system. All of that data will flow into updated model runs and the ensemble spread. The spaghetti plot that currently looks like discarded pasta will begin to narrow. What forecasters and emergency managers are hoping for, in the deepest and most professional part of themselves, is not necessarily the best possible outcome, though they hope for that too, but the fastest possible collapse of uncertainty. Because the uncertainty is itself dangerous. Every hour that the range of possible outcomes stays wide is an hour that protective decisions are harder to make and harder to communicate. The sooner the atmosphere makes its choice, the sooner the people who need to respond to that choice can respond effectively. The storms will make their choice. They are already making it. In the complex interactions of pressure and circulation and thermodynamics that no model fully captures, but all models are trying to represent. The atmosphere doesn't experience uncertainty, it just evolves according to the physics. The uncertainty lives entirely on the human side of the equation, in the gap between what's happening and what we can measure, between what we can measure and what the models can resolve, between what the models say and what we can act on. Closing that gap, even incrementally, is what every data transmission from a reconnaissance aircraft, every updated model run, every new satellite image cycle is working toward right now. The technology is extraordinary. The effort is maximal. The stakes are as high as they get in operational weather forecasting, and the ocean beneath those storms is still warm, still providing fuel, still doing what it has always done, on its own terms, indifferent to the category distinctions that humans have imposed on its surface energy, indifferent to the models running on supercomputers, indifferent to the fear in the voices of the people watching it from above. Let's turn to something that the immediate drama of this event can obscure, which is the longer arc of how humanity learns to live with tropical cyclones, or fails to. Because the history of how coastal populations have related to these storms over centuries is not simply a history of victimhood and disaster. It is also a history of adaptation, of learning, of building, imperfectly and unevenly, toward greater resilience. That history deserves attention, because it shapes what is possible now and what might be possible in the future. The earliest systematic knowledge of tropical cyclones in the Western record comes from Caribbean peoples who had lived in hurricane-prone regions for centuries before European contact and who had developed a deep practical understanding of storm signs and seasonal rhythms. The word hurricane itself derives from the indigenous Caribbean word for these storms, a word that encoded the storm's power and danger into language. Those communities could not predict storms with instruments or models, but they had developed cultural knowledge about seasonal risk, about the signs that preceded major storms, about which coastal areas were most dangerous and which offered protection. That indigenous knowledge was largely ignored by European colonizers who built their settlements, plantations, and port infrastructure in maximally exposed coastal locations chosen for commercial convenience rather than storm resilience. The result was a series of catastrophic storm disasters across Caribbean and Gulf coastal communities in the colonial and early post-colonial period that killed tens of thousands and repeatedly destroyed infrastructure that had been built without reference to the storm environment. The pattern of building in hazardous locations, losing infrastructure to storms, rebuilding in the same locations and repeating the cycle, was established early and has proven remarkably durable. The development of modern meteorological monitoring beginning in the 19th century and accelerating through the 20th did not immediately change the fundamental pattern of coastal exposure. What it did was reduce the death toll from surprise, from storms that arrived with no warning and killed everyone who happened to be in their path. The ability to track storms, even imperfectly, and issue warnings days in advance, saved large numbers of lives compared to the baseline of no warning at all. The death tolls from major hurricanes in the 20th century, while still terrible, are substantially lower than they would have been if storms had continued to arrive without any advance notice. But the death toll reduction from better warning systems happened against a background of increasing exposure. Coastal populations grew. Coastal development intensified. The asset value concentrated in hurricane-prone coastal zones increased enormously. So while the probability of dying from a given storm intensity declined, because warnings allowed people to get out of the way, the total potential loss from any given storm increased, because there was so much more at stake. The two trends, better prediction on one hand and greater exposure on the other, have been running simultaneously for decades, pulling in opposite directions on the overall risk picture. The net result is deeply uneven. In terms of direct storm casualties, deaths from wind, surge, and rain, early warning systems have achieved remarkable results in many wealthy countries. Storms that would have killed thousands in a pre-forecast era now often kill dozens or hundreds, at least in the acute phase, because people were warned and many were able to get out of the way. In lower-income countries with less robust warning and evacuation infrastructure, the death tolls remain much higher for comparable storm intensities, because the same physical event produces very different outcomes depending on the capacity of the human systems that respond to it. The global divergence in storm outcomes is one of the starkest illustrations of the relationship between economic development and disaster resilience. It is not that poor countries experience worse storms. Storm intensity is determined by atmospheric physics, not by income levels. It is that the human systems that determine whether a storm's physical energy translates into mass casualties are deeply dependent on resources, infrastructure, and governance capacity that are not equally distributed. This matters for the current event because the affected region, wherever the storms ultimately impact, will include significant variation in the capacity of different communities to prepare, respond, and recover. The same storm hitting different neighborhoods in the same city can produce radically different outcomes depending on housing quality, infrastructure condition, access to transportation, and the depth of local support systems. The storm doesn't discriminate. The vulnerability does. Something that rarely gets discussed in storm coverage but that is increasingly recognized within the emergency management community is the role of pre-existing stress on the people and systems that storms strike. A community that was already dealing with economic distress, housing insecurity, health challenges, or degraded infrastructure before the storm arrives is not starting from the same resilience baseline as a community that was in better shape going in. The storm doesn't encounter a blank slate. It encounters a system that already has capacity constraints, already has people stretched thin, already has infrastructure that was aging or inadequate before the first rain band arrived. The compounding effect of multiple stresses is something that disaster researchers have been working to better quantify, because the aggregate vulnerability of a community is not simply the sum of its individual vulnerabilities. Systems under stress interact in ways that amplify each other. An overtaxed hospital system can't absorb a surge of storm-related injuries as effectively as one that had capacity to spare. A road network already congested and poorly maintained doesn't handle evacuation traffic as safely or efficiently as one that was in good condition. A population already dealing with elevated anxiety and diminished social cohesion from prior stressors doesn't mobilize and support each other through a new crisis as effectively as a more stable community would. Recognizing this doesn't change the immediate response to the current event, but it shapes how we should think about what adequate preparation for storm events actually requires. It is not just about having better forecast models or cleaner evacuation routes, though those matter. It is about the overall state of community resilience, the social, economic, physical, and institutional resources that determine how a system absorbs a major shock and recovers from it. Building that resilience in communities that face significant tropical storm risk is work that has to happen long before any specific storm is forming in the Atlantic or the Pacific. A lot of that work is happening. It just happens slowly, underfunded, and largely invisible to the kind of coverage that follows dramatic events. The communities that have invested in stronger building codes and better land use planning and more robust social support systems are harder to see in ordinary times than they are after a storm, when the houses are still standing and the neighborhoods are still functional and the people have fewer deaths to mourn. The absence of disaster is invisible in a way that disaster itself never is. The scientists and engineers and emergency managers and community planners who work on resilience outside of the immediate crisis moments know this. They work against a perpetual background dynamic in which attention and resources flow toward the acute event and then ebb away, before the longer-term work of actually reducing vulnerability is complete. The funding cycle for disaster preparedness has a familiar shape in many places. A major disaster generates urgency and resources. Those resources partially address the most visible vulnerabilities. Attention fades as the disaster recedes from memory. Preparedness investments get cut in the next budget cycle as other priorities compete, and then the next disaster arrives to reset the cycle. Breaking that cycle requires the kind of sustained political will and public attention that is genuinely difficult to maintain in the years between major events. The communities that have broken it, that have maintained and incrementally improved their preparedness, infrastructure even in the quiet years between storms, are the communities that perform best when the next storm arrives. The investment is real, the returns are real, they just don't show up in a way that drives news cycles. For now, the storms are still out there, the interaction is still unfolding, the models are still disagreeing about the final outcome, though the disagreement is narrower than it was. The reconnaissance aircraft are still making their runs. The emergency managers are still on their phones. The families in the potentially affected areas are still watching their local forecast, still trying to decide. The next satellite image cycle will bring new data. The next model run will update the ensemble. The next reconnaissance flight will measure the central pressures of both systems and transmit those measurements back in real time. The forecast will evolve. The uncertainty will collapse slowly and then at some point quickly. And when it does, the scope of the disaster that these storms produce or don't will become clear with a finality that the preceding days of uncertainty made impossible. Whatever that outcome is, the full weight of it will be felt by real people in real places, not as a statistic or a model output or a point on a probability distribution, as the thing that happened to them, as the thing they survived or didn't, as the shape that their lives take on the other side of these next few days. The atmosphere is doing what it always does, operating on scales and timescales that dwarf human experience, following physical laws that don't bend to urgency or prayer, or the best models that human ingenuity has produced. The ocean gives up its heat. The pressure falls. The winds tighten around the centre. The eye wall churns. The spiral bands reach outward across hundreds of miles of open water, and on the coast, in the emergency operations centres, in the communities where people are making decisions about whether to stay or go, in the homes where families are looking at weather apps and trying to understand what the probability cones and storm surge maps are actually telling them about their specific situation, in the cars on the evacuation routes, in the shelters filling up ahead of schedule, in all of those places. The next hours matter in ways that will be measured not in model skill scores or ensemble spread statistics, but in the most irreducible terms there are. The forecasters are doing their jobs with extraordinary skill under conditions that test the limits of what current science can provide. The emergency managers are doing their jobs with the knowledge that every decision they make right now will be scrutinized in the aftermath, and they are making those decisions anyway, as well as anyone could make them with the information available. The communities in the potential impact zones are doing what communities do when major storms approach. They are preparing, they are worrying, they are helping each other, they are watching the sky. What the sky does next is still, in the most important sense, unknown. The tools we have to reduce that uncertainty are the best that have ever existed. They are not enough to eliminate it. That gap between our best tools and the full complexity of the atmosphere is where the story of these storms is still being written, in warm water and rotating winds, in a language that forecasters have spent their careers learning to read and that the atmosphere has never agreed to simplify. 2 storms, 1 ocean, a world watching. The next several hours will tell us more than the last several days have. Until then, the only honest thing to say is that the people who watch these systems for a living are watching very, very closely, and they are not watching casually. They are watching with everything they have, hoping that the collapse of uncertainty, when it comes, lands on the better end of the range. It doesn't always, but sometimes it does, and the only way to know which side of that divide this event will fall on is to stay with it, hour by hour, update by update, as the atmosphere finishes writing a forecast that no model has been able to write for it. The storms will resolve. They always do. The question that will define everything that happens in the weeks and months after this event is the same question that has always defined major storm disasters. What did we do with the time we had before we knew for certain? Because that time, the time of uncertainty, the time of preparation, the time when the worst case is still only a case and not a certainty, that time is the most valuable time there is. And right now there is still some of it left.